It can be shown that the magnetic field at a point in space due to a long, straight wire carrying current I is given by mu naught times I divided by 2 pi r, where the direction is tangent to a circle centered around the wire given by the right-hand rule, and r is the distance from the point to the wire. Well, as you know, the source of all magnetism is moving charge. So if we have a current, which by definition is the movement of charge, then that current generates a magnetic field. And we could show that that magnetic field is given by this formula. Let's start off with a sketch. Here we have a long, straight wire. Let's place this wire on the x-axis of our coordinate system for convenience. We will center the wire about the origin, so the vertical axis is the y-axis, and the z-axis will be the axis coming straight out of the screen. We want to find the magnetic field at a point in space, a certain distance away from this long, straight wire. So because this is a long, straight wire, let's just model it as infinitely long. And what that means is, in practice, that the length of the wire is much greater than any distance away from the wire. So let's say we're going to look for the magnetic field at a point, a distance d away from the wire. And we will put this position or this point on the y-axis. Since this is a long straight wire, the y-axis can, for all intents and purposes, be considered to be going right through the center of this wire. And this coordinate is the coordinate 0, d. Let's also just say that this wire is of length L. So we will have L spanning the length of the wire, and what we're going to say towards the end is, since it's a long straight wire, we're just going to allow L to go to infinity. Now that means the left end of this wire is at coordinate minus L over 2, and the right end of this wire is at coordinate L over 2. Looking ahead, to make the mathematics simpler, and hindsight will show how it makes it a little bit simpler, I'm just going to define lowercase l to be equal to L over 2. So that means the left end is at coordinate minus L on the x-axis, and the right end is at coordinate L on the x-axis. This wire is carrying a current. So let's just say the current is going in the positive x direction. We will indicate that current with the I right here. Now the Biot-Savart Law for current carrying wires says that an infinitesimally small amount of current in a segment of wire produces a small amount of magnetic field given by mu naught I, being the current, over 4 pi times the cross product between the segment of wire, which we'll call dl, and a unit vector that is representing the direction of the point in space to our small segment of current over r squared. So what is dl? Well, we're going to break this wire up into a very small representative current element. We'll put that current element right here. This small segment of wire has a small current element, and this current element has a displacement of dl for basically that length. dl in a small amount of time. That dl produces a magnetic field at all points in space surrounding it. Now, since we are looking for the magnetic field at a distance d away from the wire, we will just indicate that the current element's contribution at that point. So this distance right here will be the distance from the small representative current element to our point in space. Now, let's go ahead and label a couple of things. You might already be recognizing what we're going to do with this. Ultimately, we're going to have to integrate, and we're going to need to express our variables in terms of the geometry of this problem. So R, for example, is really the hypotenuse of a right triangle where the sides are D for the vertical side or the vertical leg of the right triangle, and the horizontal leg of the right triangle we will say is given by the variable minus x. This means that R can be found from Pythagorean's theorem to be equal to the square root of x squared plus d squared. And notice that dl is in the positive x direction. So let's go ahead and represent dl in terms of x as well. So dl is equivalent to dxi hat. This means that we could represent the infinitesimally small contribution to the magnetic field as mu naught I over 4 pi dxi hat crossed with r hat over r squared, and r squared is given by x squared plus d squared, and that's really the square root squared. Since the current is parallel to the wire, if we did the right-hand rule, we would see that the magnetic field forms concentric circles around the wire. So this would be a magnetic field line that passes through the point at which we want to evaluate the magnetic field. And so at that point where we're evaluating the magnetic field, we would know that the magnetic field is tangent to the circle, and this magnetic field vector represents the tiny contribution of magnetic field due to our small amount of current. So from this diagram, we would see that the magnetic field is pointing along the positive z axis. Well, we're not too far actually from evaluating this magnetic field. If we integrate our magnetic field differential, well, really integrate both sides of our equation, we would have the integral of mu naught I over 4 pi dxi hat cross r hat over x squared plus d squared. Now, what are our limits of integration? Well, our limits of integration is based off of the geometry of the problem, and specifically the length of our wire. So since the integral is over dx, that means we're going to integrate from minus L, the left end of the wire, to L, the right end of the wire. So what we have to do now is decide what to do with this cross product here. Now, because we already know the direction of the magnetic field given to us by the right-hand rule, instead of evaluating the cross product, I am just going to recognize that the cross product of two vector its magnitude is given as the product of the magnitudes of each vector times the sine of the reference angle between each vector. So for this problem in which we have I hat cross r hat, well, what is r hat? R hat is that unit vector that points in the direction of the relative position of that point on the y-axis to our representative source charge element on dl. So I hat cross r hat is then just the magnitude of I hat, and remember the magnitude of a unit vector is equal to 1, so that's just going to be 1, times the magnitude of r hat, which will also be 1, times the sine of the angle between our current element, I'll just call this dl, and r. Well, then this is just sine of theta, and let me just go ahead and call that LR, just a few less variables to write. So the magnitude of I hat cross r hat is just equal to the sine of the angle between those two vectors. Okay, so what two vectors you're wondering we're looking at? Well, if we look at the picture, we have dl going in the positive x direction. We have r hat pointing to our point in space. So our angle theta LR is just the angle between those two vectors. I'll just go ahead and add that to our picture, theta LR. So what is theta LR? Well, we can get this from our right triangle. Remember, we had R, D, and X. This triangle is similar to the triangle given to us by our DL vector and our R hat. So we could look at this and recognize that the sine of this angle is equal to the opposite side over the hypotenuse. And that opposite side is D, and the hypotenuse, remember, is x squared plus d squared, or rather the square root of x squared plus d squared. So this means that we could write the magnetic field is the integral from minus L to L mu naught I over 4 pi times the sine of the angle between L and R over x squared plus d squared, and we have the dx right here. So then this is the magnetic field is equal to minus L to L mu naught I over 4 pi. We just said that the sine of the angle is equal to d over the square root of x squared plus d squared. That is the sine of the angle right here. And this is dx over x squared plus d squared. Now, mu naught is a constant, I is a constant, d is a constant, 4 pi is a constant. So those all come outside of the integral. And we are left with dx over x squared plus d squared to the 3/2. We could look up this integral in an integration table. Or if you're hardcore, you could just do a trig substitution to figure out what that integral will evaluate to be. But I'm actually going to look it up in an integration table. And when I look it up in an integration table, I get that integral for the magnetic field is mu naught I d over 4 pi, and that integral evaluates to x over d squared times the square root of x squared plus d squared. And that is evaluated from minus L to L. Now the magnetic field is a vector, and I see that I've left off my direction of this magnetic field for the last couple of steps, so I'm going to reinsert it. Remember, our magnetic field was pointing parallel to the z-axis, so that is in the k hat direction. So I will add the k hat here, the k hat here, the k hat here, and the k hat here to take care of our direction. So now let's go ahead and evaluate the endpoints of this integral. So we have the magnetic field is mu naught I d over 4 pi. Oh, look at this. A d in the numerator cancels with the d in the denominator. So I could just simplify this down. So we have mu naught I over 4 pi d. And then now, plugging in our limits of integration, we have L over the square root of L squared plus d squared minus a minus L over the square root of minus L squared plus d squared. I see that we have an L minus a minus L, which is a positive L. That gives us 2 in the numerator, so 2 mu naught I over 4 pi d, and we have L over the square root of L squared plus d squared k hat. This is not our answer because we solved this as if the wire was finite. And the problem said we have a very long wire. And that's code word really for the wire is so long we can treat it as infinitely long. The reason why that approximation is important for this one, it's because we had set our origin to be the center of the wire. And we're saying that the magnetic field at any point, a distance d from the wire, will be the same value everywhere, a distance d from the wire. Now, that's not true for a finite length wire. For a finite length wire, the magnetic field, let's say, immediately above the left end at a distance d, will be different than the magnetic field above the center of the wire. So by saying it's a very long wire, we are saying that the distance from the point to the wire is much, much less than the length of the wire. And what that allows us to do, it allows us to say that the magnetic field at any point, a certain distance away from the wire, will be the same. So there is no left end if this is a very long wire. There is no right end if this is a very long wire, because we're considering it to be infinitely long. Yes, this is an approximation, but this approximation works very well for points in space that are very close to the wire. With that said, since we're assuming this is an infinitely long wire, so in saying that, we could say that the magnetic field is mu naught I over 2 pi d, where I recognize that the 2 in the numerator gets rid of a 2 in the denominator, and this is L over the square root of L squared. Now, the reason why I don't have the d squared in the denominator is because, remember, we're saying L is much, much greater than d. And remember, we're defining little l to be L over 2. So that's also going to be much, much greater than D. Since it's much, much greater than D, the L squared under the square root overpowers the D squared. So basically the D squared is negligible in comparison to L squared. Now, what this allows us to do is we see that we have an L in the numerator cancels with an L in the denominator. And we now have the magnetic field is equal to mu naught I over 2 pi d. So notice what we have here. The magnetic field at a distance d away from the wire is directly proportional to the current in the wire and inversely proportional to the distance d away from the wire. Since this is a general result that applies to any straight wire when we evaluate the magnetic field at a point close to that wire, let's go ahead and generalize that d variable. It's typically more convenient now to use the variable lowercase r to represent the distance away from the wire. And instead of saying k hat, because k hat is tied to our particular choice of coordinate system, we could say the direction of the magnetic field is the direction given by the right-hand rule. And in saying that, we could write that the magnetic field is equal to mu naught I over 2 pi r, and I'll just write this to represent the direction given by the right-hand rule. Notice from this that the magnetic field at a point in space due to our long wire is directly proportional to the current flowing in that wire and inversely proportional to the distance away from that wire. If we were to sketch this magnetic field as a function of distance, that it would look something like this because of that inverse relationship. And remember, being a current-carrying wire, the magnetic field forms concentric circles. The closer you are to the wire, the stronger the magnetic field. But the farther away you get from the wire, the weaker the magnetic field, following that inverse relationship with the distance. So here is our result for the magnetic field a distance r away from a current carrying wire.